Alright, hello everyone. Today we will dive into the world of memory cache mapping techniques, a cornerstone of computer architecture. We will explore how cache memory bridges the speed gap between the CPU and the main memory, and the clever strategies used to manage data efficiently. By the end, you will understand the trade-offs between different mapping techniques and how they impact system performance. So let's get started. What is cache memory? Cache memory is like a high speed pit stop for the CPU. It's a small but incredibly fast memory unit sitting between the CPU and the slower main memory, which is the RAM. Its job: store frequently accessed data and instructions so the CPU doesn't have to wait for the RAM every time. Think of it as keeping your favorite tools right on your desk instead of in a distant storage room. This drastically cuts down the average access time, and boosts overall confidence. Now we move on to the importance of what cache mapping. Cache memory is limited in size, so we need smart ways to decide where data from main memory should live in the cache. That's where mapping techniques comes in. They minimize cache misses, those frustrating moments when the CPU can't find data in the cache and has to fetch it from slower RAM. So for this, the key terms to remember are cache, line or block, which is the smallest chunk of data transferred between RAM and cache. A tag, which is a unique ID for the main memory block stored in a cache line. And an index which is point an index that is point to the specific cache set or line. And then an offset, it locates the exact word within a cache line. With this in mind, let's look at the three main mapping strategies. So first of all, we have the direct mapping technique. The direct mapping technique is the simplest approach. Each block from main memory is assigned to exactly one line in the cache, calculated using a modulo operation, which is cache line equal to block address modulus cache size. This is fast and easy to implement, like assigning each student to a fixed seat in a classroom, but it has a downside: conflict misses. If two frequently used blocks map to the same cache line, they will constantly they will constantly kick each other out, even if other lines are empty. It is efficient but inflexible. Now we move on to the fully associative mapping. For the fully associative mapping is the opposite extreme. Here, any block from main memory can go into any line in the cache when the CPU requests data. All cache tags are searched in parallel, like checking every locker in a gym at once. This gives the lowest miss rate since the cache is fully utilized, but searching every line in parallel requires expensive hardware, making it impractical for large caches. You will see it in small, specialized caches like TLBs, which is the translation look aside buffers. Now move on to the next one, which is the set associative mapping. For set associative mapping, it strikes a golden balance. The cache is divided into sets, each holding a few lines, for example a two-way or a four-way. A block maps to a specific set but can occupy any line within that set. Think of it like grouping lockers to sections. You only search one section, not the entire gym. This reduces conflict misses without the hardware cost of fully associative mapping. It's why most modern CPUs use these techniques. Now for the comparison. For the direct mapping, it's simple and fast but suffers from conflict. For the fully associative, it avoids conflict but is complex and costly. And for the set associative, it offers a sweet spot, which is medium complexity, low conflict misses, and reasonable hardware cost. The choice depends on your priorities, which is the speed, flexibility, or cost efficiency. So now we move on to the next slide, which is the cache replacement policies. When the cache is full, how do we decide which block to elevate? That's where the replacement policies come in. So we have some common strategies that include LRU, which is least recently used. It evicts the block untouched for the longest time. And we also have the FIFO, which is the first in, first out. It removes the oldest block regardless of use. And we also have the random. For this, it picks a victim at random, surprisingly effective. The goal is minimize future misses by predicting which block won't be needed soon. Now we move on to the cache write policies. Writing data to cache introduces another challenge, consistency with main memory. So we have two main policies that handle this. So the first one is write true. For this, data is written to both cache and RAM immediately. Simple but slower due to RAM latency. And we also have the write back. For this, data is written only to cache initially, and then the RAM is updated later when the block is evicted. Faster but requires tracking dirty blocks. So in conclusion, to wrap things up, the cache mapping helps decide where data is stored in the cache using direct, fully associative or set associative techniques. Replacement and write policies also play a big role in keeping things fast and efficient. Understanding all these techniques is super important if we want to design better and faster computer systems. Thanks for watching or listening, and I hope this was helpful.